So I would like to speak about radial distribution of elements in galactic disks, mainly about its central part, but more broadly, what do we know about galactic disk chemical properties? So here you see my colleagues, my collaborators from several countries, and our tool. So we are using Galactic Cepheids stars. They are yellow supergiants, and we use their spectroscopic analysis to derive chemical abundances in these stars. So why we selected Cepheids? First of all, they are young population. They belong to the thin disk, and they are quite luminous objects and can be seen at the large distances, and we can probe at the large distances, of course, with these stars. They obey period luminosity relation. This is very good because in this case, we can have a possibility to derive their precise distances. So, and what is important, spectral lines of many chemical elements can be seen in their spectra, in visual part, infrared part, and this gives us possibility to derive abundance distributions in the disk for about 25 elements. It can be even more, but we used the set of 25 elements, mainly from carbon to dysprosium. So this is view of our galaxy edge on. Don't be scared, this is written in Ukrainian. So our Cepheids are distributed in the plane of our galaxy, more precisely in the thin galactic disk. So where we collected our material? During 20 years, we selected spectra from the telescope of the intermediate sites and larger sites, VLT, for example, Hubble-Eberle telescope. This list, you can see it here. So our material, in total, we have collected more than 1,500 high-resolution spectra for more than 400 classical Cepheids. It is, this value is more than half of Cepheids that are suspected to exist in our galaxy. So we have very good statistics with these stars. So spectra were analyzed both with local thermodynamical equilibrium approximation and without it, non-LT, so-called non-LT approximation. It's very complicated spectroscopic method, but we have a group, very good group, and we are doing this work for many years. So we are experienced guys. So precise galactocentric distances for program stars can be calculated from this simple equation. Here, galactocentric distance of the star, our sun, is about 8 kiloparsecs from the center. This is heliocentric distance from our sun, of course. B is galactic altitude, and L is galactic longitude. So this is distribution of our stars in the plane of our galaxy. You see sun is here on the cross of two lines. We are here. Here is center of galaxy, but this is quite old picture. I will be speaking about central parts, so about stars which are concentrated here. So by analyzing this sample of stars, we obtained, as I told you, the distribution of the disk of 25 chemical elements, but we are mainly interested in the iron element. So this is usual destination. This is brackets, square brackets. They mean that we use concentration of iron per concentration of hydrogen, logarithmic scale, and this value is normalized to the solar ratio. So we see we covered the range of metallicity. So iron content always is called as metallicity. So metallicity from minus 0.6, it means that heavy metals, iron, for example, is about 4 times, 5 times less than in our sun. And 0.2 is more than in the sun. So we constructed for this sample of stars 2D abundance distribution of iron in galactic disk. Here we are, our sun. Here is center of the galaxy, and as you see, we covered it in our plane, in the plane of our galaxy, square about area about 10 kiloparsecs per 10 kiloparsecs. It's huge value, I would say, 10 kiloparsecs by 10 kiloparsecs. And blue color testifies to very low abundance, underabundance, and red areas indicate about high abundance. So this is overabundance. No, it is expected that abundance should increase toward the center of our galaxy, but it is not axioma, I would say. So if we reduce position of the stars in 2D diagrams using this formula, as I showed you before, then we get the radial elemental abundance distribution along the line. So we should put all the stars from plane to the one line: galactic center, sun, galactic anticenter. This distribution can be described by abundance gradient, very important value, which is one of the input parameter for any galactic chemical evolution model. Very important parameter. Linear approximation for our data in the range of the galactocentric distances from 4 to 16 kiloparsecs is the following. What we have got: minus 0.055 dex per kiloparsec, minus because metallicity increases toward the galactic center as galactocentric distance decreases. And we see it in this picture. All our stars, galactocentric distance, metallicity. We are here about 0 and about 8 kiloparsecs. Our sun is here. So as you see, with this sample, we covered galactocentric distances from 4 to 16. This is not 1. Here we have 16 kiloparsecs. But this is simple linear approximation. If we apply, for example, Love's method, so method of local regression, we can see some kind of bands, some kind of tiny features which cannot be seen here, but this is later. So now, what we have at the very center of our galaxy, we expect to have their intermediate mass black hole. At least many astronomers believe in this. This is model of our galaxy, a polar on. Here our sun, solar circle, orbit, 4 arms, but it's discutable because some people believe that we have only 2 arms, spiral arms, but I put here 4. And here we have very important feature of our galaxy. This is Galactic Bar. So here the semi-axis of Galactic Bar is about 3 kiloparsecs. This is important, I will tell you why later. So to explain our data, observational data, we elaborated simple but very effective model of galactic chemical evolution. So input data for galactic spiral structure model. We need to describe these 2 values. First of all, this is angular velocity of the disk, angular velocity of the disk. Disk consists of stars and gas clouds. And angular velocity of the disk it's distributed with its function of the galactocentric distance. It describes Keplerian rotation. So with increase of galactocentric distance, angular velocity decreases. It's almost the same as we have in our solar system. The more distance of the planet from the sun, the less angular velocity and linear velocity, of course. And this is angular velocity of the spiral pattern, of the spiral arms. Spiral arms rotate as rigidly. They rotate rigidly as, for example, the wheel of the bicycle. So, for example, if we put this in the plot, here thick line represents the angular velocity distribution versus galactocentric distance. It's almost Keplerian, because for the open cluster, global clusters and galaxies, for example, it deviates from the Keplerian because maybe of the dark matter. But for our case, we use schematic description. So for our aim, it's enough to suppose that we have Keplerian distribution. And also we put here a rigidly rotating spiral pattern. Now in literature, two values are discussed. First, 20 kilometers per second per kiloparsec. Here, you see, this is a rigidly rotating spiral pattern. Its angular velocity doesn't depend upon the galactocentric distance. And second value, 28. In our model, we consider two values, but then I will show you results for 20 kilometers per second per kiloparsec. Where we have for example, let us use 20, where this value intersects with Keplerian rotation of the disk, we have co-rotation resonance. So it means that here disk and spiral pattern rotate with the same velocity. Inside co-rotation circle, co-rotation is circle, of course. Inside this circle, disk rotates more rapidly, more fast than the spiral pattern. Outside, on contrary, disk rotates slowly, more slower than the spiral pattern. It's very important. And here you see theory also operates with epicyclic velocity, frequency, excuse me, which gives us condition for inner Lindblad resonance in red, here co-rotation resonance in red, here inner Lindblad resonance in red, and outer Lindblad, here, it is here, resonance, Lindblad resonance. It means that spiral pattern can exist only between inner resonance Lindblad and outer Lindblad resonance. Outside these values, no spiral pattern. Okay. Again, this is schematic view of our galaxy, and we now, I would like quickly to present you the simple approximation that we use to describe our observational data. So we used three differential equation. First is for concentration, change of concentration of the stars with time, change of concentration of the gas. Gas is consumed to produce stars. It's understandable. And stars produce metals, and metals, heavy metals, for example, we consider it alpha elements and iron. This is described by Z. Z is metallicity. So, very important value here is psi. Psi is the star formation rate. How many mass of the sun we have in our disk per 1 gigayear. So, and we can start solution of this equation with initial conditions. But the problem was the following. normally people doing the galactic chemical evolution modeling, they use simple approximation as usual. Star formation rate depends upon the concentration of the gas power to K. K could be 1 or 2. Kennicott, for example, insists that it should be 1.6 and nothing more. People forget about spiral patterns. We know that spiral patterns should play extremely important role in the galactic formation. But people say, no, okay, so star formation rate depends only on the concentration of the gas in the disk. We improved this situation and improved and modified the star formation rate by taking into account spiral arms. So we modified value for star formation rate by including term delta. So I will not explain what does it mean epsilon and etc. Very important term that we included into consideration is difference between angular velocity of the disk and angular velocity of the pattern. So this means that at the rotation circle, when delta is equals to 0, at the rotation circle, we have only this star formation presentation. So delta is 0. But if the distance increases from the rotation circle, the contribution of this term increases, of course. So the further we are located from corrotation resonance, corrotation circle, the larger will be difference between angular velocity of the galactic disk and spiral arm. And therefore, the higher the difference in the linear velocities, the higher difference in the angular velocities, the higher will be difference in the linear velocities. Thus, this gas from the disk penetrates the arm at the higher velocity. So the higher velocity, higher the gas compression, and higher efficiency of the compressed gas for fragmentation. The higher the star formation rate, of course. Where the star formation higher, there are gas consumed more quickly. And we see this on the next slide. For example, this is concentration of the gas in the disk. And you see here we have, for example, for 20 kilometers per second per kiloparsec angular velocity. It is here, about 11 kiloparsecs from the center. We hear that consumption of the gas is not very high, but it increases as we move from the corrotation resonance. And here Lindblad, inner Lindblad resonance, here the outer. So here no spiral arms, and here also. And this is also depicted in the metallicity. And you see metallicity has some minimal value at the 11 kiloparsecs. Now we can compare our data, observational data. It is, as I told you, this is radial distribution of iron in our disk. And we compare with our calculation, and we see quite good agreement. This is for iron, this is for alpha elements. So alpha elements is oxygen, for example, magnesium, silicon, sulfur, calcium, titanium. Quite good agreement, fine. But what about galactic central region? We see that we started from 4 kiloparsecs. At that time, we hadn't any data about stars near to galactic center. In the thin disk, people did work, for example, for bulge stars. Okay, but bulge stars could be very old, but we are speaking about young population in the thin disk. But nobody observed young stars in the thin disk at the galactic center. So first we were able to find 2 Cepheid stars situated very close to galactic center. We observed them with Canada, France, Hawaii telescope. These are stars, 2 stars. One is situated at galactocentric distance 3 kiloparsecs, and second even closer to galactic center, 2.5. Fine. This was published several years ago. And we constructed now radial abundance distribution for several, I will show for several elements, including these two stars. You can ask me, oh, what is this at the very center of galaxy? Yes, these data are from bulge stars, not from thin disk. This is, for example, for silicon. This is for sulfur, no data in the literature for bulge stars. This is literature data. This is not our result. Okay, so silicon, calcium, titanium, and what is important, iron and oxygen. You see, as I told you, gradient is negative. So as galactocentric distance decreases, metallicity increases. This is logarithmic scale. We should take this in the mind that it is in fact exponential increase, but logarithmic is more or less linear. And here are our two stars. And this is iron distribution with interpolation. As I told you, for example, if we use lowest interpolation, we have such not very linear. I should tell you that each point has points have not the same weight, because this one star, for example, has only one spectrum. Another star can have 5 spectra. So the weight should be higher. So it's weighted data. And this is non-LT, for example, as I told you, we also can do non-LT calculations, abundance determination, and this is for oxygen, very important information. Oh, okay, this is galaxy, very known figure. So we are here, and what is the problem? How to see stars near the center? Because they're very dim, they are obscured, they are very faint. Even this, they are supergiant star, but so many dust in the disk, this star can be, for example, less higher than 22, 24 magnitude. So it's unreachable in visual part of the spectrum. And but Dekani and Matsunaga with colleagues succeeded to observe in infrared photometry, infrared, not spectra, infrared photometry. We are here our sun, the center of galaxy, stars, Cepheids, of course, our Cepheids, here sun, center of galaxy. They succeeded to observe 4 stars at the very center of our galaxy, and many stars even behind the center of our galaxy. This was terra incognita before, but now it's available, but it's photometry. But we succeeded to observe several stars with NASA infrared, 3-meter infrared telescope facilities, ice-shell spectrograph, new spectrograph, and we obtained the high-resolution spectra for the 4 Cepheids in vicinity of the galactic center at galactocentric distances less than 1 kiloparsec. So I show you these results. This is our results. These are our results. So, so this is for oxygen, silicon, magnesium, calcium, sulfur, titanium, and finally iron. So you see, interesting feature. So metallicity increases toward the galactic center. Then we have some kind of plateau, and then drop with positive gradient toward the galactic center. At the galactic center, metallicity is practically the same as in vicinity on our sun here, 8 kiloparsecs. You see, it's very strange. Very strange. Existing models, Kaviccia, Fu, Minchev, they produced their theoretical distributions before we derived this abundance for galactic center. But you see, none of the existing theories can explain the central abundances in our galaxy. This is for iron, this is for oxygen. None of the existing theories. So, the chemical properties of the central zone of the seen disk today is perhaps the most interesting and intriguing question for galactic hemodynamical models. Conclusion, but not probably end of the story. We try to go behind the center of our galaxy. So, elemental abundance distribution in the young galactic thin disk stars show that the rise of abundance with galactocentric distances decrease is not simply exponential, not simply linear, for example, in logarithmic scale. We discovered a plateau-like structure in abundance distribution at about 2-4 kiloparsecs. 2-4 kiloparsecs. It is here, 2-4 kiloparsecs. Okay, you can say statistic is small, but it's difficult to find Cepheids at these distances. We cannot do this now. And where elemental abundance is about 2-3 times, you see 2-3 times is about 0.4 in logarithmic scale. It's 2 or 3 times larger than in vicinity of the sun, in our sun also. And elemental abundances in the galactic disk drop at the very galactic center up to the value typical for this solar position, sun position. It is here. It's strange, but it should be explained by very elaborated models of the galactic chemical evolution. Up to now, this was practically unknown for us. So, and this work was made in observatory of Odessa, and Odessa situated in the Odessa Observatory. The Odessa Observatory is situated in Odessa city. Obrigado pela sua atenção.